Okay, today is March 14th. Currently right now it's 9:23 p.m. I'm going to give you all a representation for the whole system itself. This is a broad behavior simulation. To get this whole solar panel in a gist, we have a solar panel here which consists of these sensors, a bypass diode, which diode just for the current itself to be redirected. Yes, there's going to be voltage drop, but in a matter of the input voltage, but we do have a relationship here as we're running the voltage. But we have a standard average radiance. The average radiance for watts per meter squared is 1,000 watts per meter squared radiance. For more sensitive objects would be more higher, which is like 1,300. More insensitive shading and inefficiency will be lower, 500 to 1,000. Temperature is a consideration. We have a radiant heat here. There's no, I stated a variable. These are just basic values. I did not have time to focus on it, and this is Boltzmann's constant. We could say 0.05. Constant temperature 293.15 and 8.55. Those are the values there. This capacitor is for filtering purposes. I did the math. The math is within the document. I have a series resistance. Any capacitor that is not affiliated within a boost or buck converter is going to have a default of 0.02 series resistance internally. There is some resistance within capacitor. Then within capacitance, I assumed trying different values. The assumed value that best fitted was 22 microfarads. Here I have another one, 10 microfarads. I could switch it to 22. Really no relative difference. That this solar panel connects to here. Filtering, this is for when there's ripple effect, it filters it for the current. Typically, and the voltage. Current sensor has to be within the lines. Voltage sensor could be across. This has to be connected with the circuit. If not, you short circuit and blah, blah, blah. This is a buck converter, a boost converter. This has a conventional MOSFET with a threshold. I customized it for my MPPT, but when we actually have put this in practice for an actual charger, which like the BQ79285, I think it was called, the Texas Instruments, it has built in, and we can just really just put in I2C communication, Raspberry Pi, and then connect it via there. Right now, currently we have, this is all situated in the math here in the document. I'm not going to go deep into it because it's already stated in the document. But here we have boosting converters. These are our values. We have a conventional standard 0.01, off-state conductance, LC parameters. Within the math stated these values. Capacitor we have, and this is ripple current. It's not good, we're getting a medium. About, it negate the mean on this one because it's like fliction out, so we're getting about 44 milliamps, which is not really high for output, but we're actually getting a reverse biased for 1 amp when we're fluctuating the battery into this for charging. So the output actual voltage is actually 13.3 volts, which is some threshold above. If you do the math here, from that conventional voltage here coming out from the solar panel is 11 volts. If you do the math here, we have four series here, one parallel. Conventional built-in diode, this is 30 square meters. We'll see our results after this. our battery valence. These are all our values. This is SOC. SOC means state of charge. I have enough time. Yep, it's 5 minutes. Okay, I need to go quick because my storage is not really that good. We have our sensing, our double. This is a data type conversion. So we had a double going out, and then we have a insert value Simulink of a Boolean, or I think it was a Boolean coming out, and we need to convert it to a double. This is our measurement modulation, not modulation, monitorization. This is constant. This is just charging limit with a 20%, discharging 80%. That's the limit. So if the battery is about 20% charged, charge it. If the limit is at 80%, then discharge and not charge it. We have a temperature. But this state of charge within, if the state of charge is less than 20%, then discharge is disabled with that fault occurs, which shuts off the DC-DC. Well, I'll explain that later. What shuts off? Faults just shuts off. State if it's high, or if it's higher, or charge disabled. Boom, disable it. Charge, fault. This is OR. So if this OR gate is typically when at least one input value is true, then the output is going to be true. At least one. For not, you inverse. So if it's true or false, charging enable. So we just inverse it. Which this is really not demonstrated properly. I would have to fool on more. This is correct and basis of how it really works. Logic operator, if this, then, or false. But typically this and this and this and this and this will typically be built within the charger itself you're using, which comes in one little IC integrator circuit. And with that, we have a DC-DC bus, which is really responsible into leading into the actual voltage going inside the load or converting the load. Make sure to filter it, shut off sequence for safety procedures, and it's standard amount. Then we have our DC-DC bus, which is just the third party in this situation, to a buck converter, which we have our input voltage is about 13. It's about 13 volts. But as we did the math for a buck converter, our output is actually 4 volts. We can filter this. This is just filter. We actually have about 4 volts mean. Current we have 0.5 or 500 milliamps, 0.6, going to our load, which is a good amount with a load resistor of 10 ohms. We can run a simulation with our adjusted values, and we'll see where our result is. This is actually my first time running it with these adjusted values, so we'll see. Make sure I have enough time. Okay, so we'll see our output here. Still getting 13.15. We're getting a little change here, little decrease. Current should be, yep, filtered. We're getting about 200 milliamps. Okay, what about our input voltage? Fluctuating in and out. Spiking, threshold about 1 volt. Current is going to be spiking like a mother. Or no, are we getting... Yeah, we're getting a very low ampage. I need to adjust the capacitor and value for it, which is really good at meaning decreasing power. So if we have a ton of them, so like here, oh wait, no. So we're gonna have, I need to filter this because this started I need to filter it because you're seeing a negative value. That's just negating. So we're actually got literally one, or that's surface charge, sorry. So we literally got 2 watts coming through, which is relatively good. Heating aspect, let's see the heating. From that, okay, I need to adjust that. That's just standard. That's not adjusting properly. I need to figure out the heat aspect. Still. Okay, that's good. DC bus, what's our output DC voltage from the battery? Should be kind of the same, not shut off. If it's shut off, then nothing's charged. We have our peak of about, yeah, still 13. A little loss, but assuming that's probably heat. Still our 30 kilohertz. Our values, oh shit, that's our actual input voltage. And what's our output? Should be, yeah, should be 4 or 5 amps. Yeah, 4.3. And we have a current about 600 milliamps. So we can just adjust this a little with the, not the load resistor. We can just internal. Let me stop this. Sorry if my hand's in the way. So doing the math, I need to mop up my paper. We can adjust these aspects. The higher this goes, the more filtered it's going to be. The lower it is, the more ripples you're going to have, the inductance. Inductance resistor should be 0.05, just assuming a little higher. Is this capacitor? Yeah, it's 22. We'll see if that makes a difference. I have enough time. Blah, 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 blah. This is a PWM generator driving the gate. Remember, any ripple you do see is not AC. It is not. It's ripple effect from the DC. Understand that. Not this. 6.45. Okay, we're getting a little adjusted more. Okay. 6. No. Negate this because this is getting tailored from the spike. So we're getting a little higher. But you just adjust those values for what you really need. And then this is your ground. I mean, this is your load. It goes to the Raspberry Pi. Further in the future, there's going to be more temperature monitorization here. I need to adjust that. I haven't really focused temperature monitorization. I was just studying on specific ICs to find. And then also, I'm going to be including Raspberry Pi IC to replicate. Yeah, you can just use Raspberry Pi IC here to replicate control aspect. I could make the full-on IC here and then connect the I2C with some Python aspect and literally simulate it. But that's currently what I have for our solar. This is for Astromechanics solar panel simulation here on MATLAB Simulink. And then next is LT Spice for actually making the circuit.